All right. Hello. It is, what is today? June 13th? Yeah, I hope so. Big announcements that matter. There will be no office hours on Thursday. I'm sorry if that breaks your heart. You just really wanted to come in and do math on Thursday, but I will be down at OU. Actually, my office hours tomorrow. I might try to slip out of here before noon if possible, but if not, I can be here till noon. So I have office hours tomorrow and Wednesday, but Thursday cannot have office hours because I will be in Athens presenting to a bunch of educators, and teachers are the hardest people to teach. So please, send me some positive energy. I'll need it. I will, however, open up appointments available for Friday since I'm not going to be here on Thursday. Even though we don't normally have class or any office hours on Friday, if you need help, if you need to come in, text me, make an appointment for Friday, 8 to noon, or even, I was here at 7 this morning. I can be here pretty early if you're an early morning person. So, any general questions, issues with Schoology? As you can see, based off our, so I'm going to delete all these slides over here. As you can see, based off our quote-unquote Sports Center feed over here, you should be relatively ready to take the Chapters 5 and 6 assessments today, at least after asking some questions. If you're not, you're slightly behind, not time to panic, but you do want to try to make a plan for how am I going to catch up and get on top of things. Remember, some chapters are bigger than others. So, try to manage that, where if a chapter's 4 sections versus 9 sections, they're obviously going to take a little bit different amounts of time to solve. So, general questions. Last opportunity. Wait time is a skill. All right. Questions on Chapter 5 materials. 5.1 would obviously be where we start. So our 5.1, getting into exponential and radicals, was all about zero and negative exponent work. Any questions on the notes or homework? If you're like beyond 5, if you've already done it, if you've already taken the test, you're ready to take the test. So I guess we should do this. Is anybody ready to turn in their notes in practice? You don't have any questions, you're ready to take the test. If so, you should do that now and get the test. Chapter 6, anybody in that boat for that? If you want to get up, come here, give me your stuff. Have a test. I'm going to pause this for a moment then, because this is going to be on what you don't know. And really, if you're not asking questions, I'm just assuming that you're good. My lesson videos were great, and everything was good. If there's issues with the videos, I got notified that in one, the sound gets a little glitchy, but it's at the end, so it's kind of okay, you can deal with it. But that nobody told me about that one yet. So you need to send me a message or an email or something so I know which one I need to go back and edit. But if there's issues with stuff, let me know. I've been improving the hardware that I use, the cameras and microphones and stuff I have. So if there's issues with stuff, let me know and I'll try to fix it. Any questions? 5.1, zero negative exponents. Any number to the 0 exponent becomes 1. Any number to a negative exponent actually means divide that many times. So 7 to the negative 3rd means divide by 7 3 times. Exponential functions, getting into the coefficient, the base, and then the exponent, where the exponent is going to be a variable. I got paper clips on the mini table if you need. Right there. Questions on this? Here you see 3 different exponentials. One going very fast, one doubling, and then one halving. So that's exponential decay. Okay, you turn in 6 also. 5.3, comparison of linear and exponentials. I've got enough coffee to sit and awkwardly stare at you guys for a while. 5.4, growth versus decay. Ava?
On the practice, actually I have 3 questions.
Is it, when we did the practice, was it G or K?
G.
Which one is this for?
Yeah. Well, 7 and 8 are kind of the same, so I guess 7.
So you need your compound, like account balance equation. So the first thing you need, I think this is in your notes, but you can also just as easily Google it, is search up compound interest. So our compound interest formula, something like this. So let's go ahead and copy this over. And we then have, you said, do you want to do 7 or 8?
7.
7. All right, smart. There we go. Now it's getting stupid. All right, so we want to take the information that we know and apply it to the formula that we know. So this goes into exponentials, and there's actually a few different financial functions. One of them is like the PERT function, which involves this value, not P equals. It'd be like account balance equals P times E to the RT. This is similar to that. E is Euler's number or Euler's number, depending on who you ask and how they pronounce it. But here, we use this function. So we are going to use the principal amount for our P. So 500 principal times 1, which is our initial amount. So of course we get back our initial amount, and what else do we get back? Well, we get back 4%, but that 4% is not actually 4% because it's 4% compounding quarterly. So this is how we turn our percent or our rate that's been given to us into an annual rate. So as you guys get into, like, who's like 15, 16, 17, around those ages? Anybody? No, we're all a little bit younger than that. So as you get to the point where debit cards and credit cards become a thing, and people are sending you these opportunities like, oh, get this special interest rate, you gotta pay attention to whether it's like a localized rate for one cycle or whether it's an annual rate. We're going to compute the annual rate by saying, well, it's 4%, but it's compounded quarterly, so number of times interest is compounded per year. While quarterly would be 4 times per year. Then still that 4 times per year times 10 years. Why do you think we do 4 times 10? What will that 40 actually give us? This n times t, because sometimes when I teach this differently. Yeah.
How many times it's compounded over the amount of years?
Yeah, that's going to tell us number of cycles that have happened. So we solve that like that, and we'll figure out our account balance. So it's all just applying this exponential work.
And then 15.
15. Revenue for giving. So this is actually easier because it's just increasing by 4% per year. So let's check out what's important here. As opposed to the last one where we knew a growth for the cycle and the cycle was less than a year, now we know the growth for a cycle and the cycle is a year. So we want to look at, we have 2.5 million. We are going to increase by 4%, so 4% more than the previous. And how much will they have 10 years from now? So I could say that the account balance for next year, or the account runs for any year. So let's say, what are we saying? Revenue. I don't like using revenue because revenue is how much you made that much. So let's just say account. Except it would be nice if I was writing with a pen. So the account after, say, Y years. How can I represent what the account's going to have in it after Y years? Well, we know it's got 2.5 million right now, so we'll just work in millions. So let's just say this is in millions. Now, to grow 4%, how do we represent that we're going to get back 4% more than we did?
You have to multiply by 1.04.
You got to multiply by 1.04. And then that happens every year. So if I have not gone a year, this is 0. To the 0 power is 1. We have 2.5 million. But this is going to be at like the amount we made at any year. How do I figure out after 10? Yeah. I gotta check if that's right. So I don't Yep.
It's raining.
It's so rainy. Yeah, you can always hear it raining here. It'll probably stop before we end class, but I'm going to run out and put my car windows up. Times the 2.5. We get 3.7. So when we replaced, and I guess I could have made this R. That can't be their total money. Only 3.7?
Well, got that 10 over on the side too.
I did what?
I wrote the 10 on the other side.
Yeah, that was my input.
Okay.
My years for 10 years. So if we want entire revenue, we would either need to sum all the first 10 years, or we could do some kind of recursive, or we could add these things to each other. We could modify our formula. But that's how we figure out the revenue on the 10th year. And then we can work back to figure out all the other years, or change our formula. Depends what you want to do.
Okay.
Right, monthly. So then we have to say the monthly increase in revenue. So if we are increasing by 4% per year,
That's where I had trouble. Couldn't find them.
so then if we change it to monthly, if it's 4% per year and we go to monthly, how could we represent, if we want a total change of 4% over the course of the year? So let's try that. But not 4, be careful, because 4%.
4.0.
So then we get 0.0033, so essentially 3 thousandths. And then you could set that up just like our compound interest formula. So the one that we used right here, essentially we'd be saying our principal amounts are 2.5 million, our 1 back from our initial, our rate divided by 12, so I could use my 0.04 divided by 12, times 12 to the 10. And then that'll work out.
Cool.
All right. More preguntas. 16? Yeah. 17? Anything else from the front before we move to the back? Right, next function that begins its rapid increase when with a tendency in 3. So Desmos would be a good thing to play with here. So our stem of our question says, write an exponential function that begins its rapid increase when x is between 2 and 3, and another when it's between 3 and 4, and another when it's between 6 and 8. So when we talk about rapid increase, well, okay, so exponential functions, we know we have y equals, didn't they say like a times b to the power of x? Wasn't that essentially our... So, here's where Desmos is great. I can now have a slider for my a, my b, and my x. So, depending on what a is and what b is, that would depend on what the output is. Now, if everything's 1, this is super lame. Because even as 1 gets raised to the power, it's just 1. So I need to change something. If I leave a as 1 and assume we don't have a coefficient yet, but play with the base, as soon as my base has a value, let me click the slider. I now start to see rapid increase. The bigger b is, what can we say about the bigger b is?
It's more steep.
Yeah, the steeper it gets, and the tighter together my rapid increase is. So if we look at this graph, and I start to increase right here, don't know where you gauge your rapid increase. I can change a, which will just pull it closer towards the x-axis or further away. And this is why I want you guys playing in Desmos a lot. We can figure things out just by literally playing. So let's say I leave a as 1. What can I do to this to move it? Well, what if I add or subtract something out here? Shift that. Like, what if I add a 5 out here? Just moves it up, right? So compared to my original, which was just this, if I add a new one, so all that adding 5 did was shift it up, right? How do I move it left or right? Because what the question's asking me to do is change where the rapid increase begins. How do I move an exponential left or right? What the b? I mean, that changes my steepness. We can play with that. It doesn't really shift where the graph is. So I can make my bigger I make my b, the tighter together my steep increase is. Right now, it looks like my steep increase is like between -0.5 and +1. Right? Like that gets pretty steep right there. What if I add something to b? So let's take away this +5. I know that that will make a vertical change. What about when I add or subtract? Oh, let's move this up a little bit. Start playing with things until you see what we want to make happen. Is this working? What if I change my b back? I have a pretty big b right now, so what if I make my b? Well, if I make this a constant, then that doesn't really help me. So what if we just choose a constant for b? So we've been playing with a slider. What if we just say it's 5? Just make this 5. So we might as well make this 5. Make them the same to start. Ooh, that did not work. I need regular script. There. Good gosh. Why do you not like this? I'm going to get rid of the A, just for on that one at least. What if I start playing in the exponent? What about shifting here? Ooh, hold up. How does purple compare to red now? Or how does red compare to purple? The red has moved to the left. So, to perform horizontal shifts to your exponential, it has to happen in the exponent. And again, it's counterintuitive. If I add in the exponent, I shift left. If I subtract in the exponent, I shift right. This is how you can change where your steep increase happens. Your base value will modify how quickly your steep increase happens. The bigger it is, the tighter together your steep increase is. As I keep getting bigger and bigger values, I might as well be making a right angle, essentially. But if I back it back down to something reasonable, like 5 to the power, and then I could shift this left or right depending on that. So I'm not going to spoon feed you this answer, but the trick is you can modify how wide your increase happens by changing the base, and you can modify where it exists, left, right, in the exponent, up, down, outside, on the end, with a constant. Does that help, Jenny? Because so there's multiple right answers. What you want to do is decide what's your base going to be. Are you going to use a coefficient, which you probably aren't because this is going to be a constant. And this would happen after the exponent happens. So right now A is just 1, so it doesn't really matter right now, but we could use it if we want to. Bigger your base is, the tighter this curve gets. So the smaller it is, let's say we make it 2, the wider this curve gets, and then I shift, move it left, right by using the values in the exponent. Anything else from 5, 4? Ooh, let's work to the future. 20 is actually represented by, anyone know? Anyone know? A parabola, but do you know what the formula would be? Nope. Y equals, or f of x equals, x squared. Is that, if you just want to, you can jot that down if you care. And then 23. Yes, but I think this is actually x equals cube root y. Because cube root of 1 is 1, cube root of 8 would then be 2. So I think x equals cube root y. Or yeah, this is y equals x cubed. It's not going to, we'll erase that. Sorry, and that threw me off for a second because what happens when you cube a negative number? You still get a negative number. So, like if I cube 2, I'll get 8. But if I cube negative 2, I'll get negative 8. Which is why this looks the same but rotated. This is a graph that you can use a 180-degree rotation to explain. If you chop it right here and rotate it 180 degrees around, it is the same graph. Anything else from 5-4? Last call. All right, moving on. Anything from 5-5? Yeah, you have practice or notes or practice?
Practice.
Okay.
10-3.
Anything from the front page of 5-5? Anybody have front page of 5-5 questions? Hmm?
Could you tell me what is something?
Yeah. Okay. So this is another great example of when we can use Desmos to help us make sense of this. what is being said here all right. So what is being said here is we have this function related to this constant, and there's some value of x that will make this function equal this constant. Now, there's two different ways that we can approach this. One way, and a way that we utilize a lot in math too, is saying, can I rewrite 27 as a power of 3? Well, yeah, for 27, this actually works out well. 3 squared we know is 9. 3 to the third we know is 27. So what we actually have here is 3 to the 2x plus 1 equals 3 to the third. So what we really have here then is 2x plus 1 equals 3, which we can then change what equation we're using and just use the exponents and say 2x plus 1 equals 3 and solve that. Because once you make the bases equal, you can just set the exponents equal. Now the other way to do this is graphically. So we use Desmos, and we set up that our one function is the 3 to the power of, which by the way, you can either click functions and I don't even know. I'll show you the way that I do exponents because I find it quicker. I think there's a way to do any exponent over here, but I do, oh, here it is, a to the b. So once you've got your base typed in, that's your a. When you click a to the b, it's going to allow you to type in whatever power you want. So now we have 2x plus 1, but you got to keep it in the power, which is sometimes you got to make this a parenthesis. Yeah. So you got to make it a quantity is normally what we say. And then we can make a second function that is just 27. And if it doesn't work, tell it I want y to equal 27. And then we can just find that intersection point, 127. So the x of 1, yeah, whether I solve it using this and say, okay, what x will make this true? Well, x would have to be 1. Or whether I solve it in the graph, saying where do they equal, x is 1. So either way I do it, I get the same answer. Now when we look at 22, this is worth showing because the whole negative exponents work. What we'd be saying if we go back to the method that I have written up here for this one is that 1/4 can be represented by a power of 2. Now a lot of people at that point, they're like, well, you're ridiculous. That's a fraction. Yeah. To turn integers into fractions, utilize negative exponents. If I do to the negative second, that actually becomes 1 over 2 to the second, which works out nicely to be 1/4. So 2 to the negative second equals 2 to the 2x minus 1, which tells me negative 2 needs to equal 2x minus 1. I can add 1 to both sides, and I get negative 1 equals 2x, and then I get x equals a negative 1/2. If you are iffy on those algebraic steps, we may need to talk because that should kind of be a natural flow at this point. I can also graph that if I wanted. So we have 2 to the power of 2x minus 1, and my constant value of 1/4 and my intersection point is negative 1/2. So you can solve it algebraically or you can solve it graphically. Thank you to the Common Core State Standards for allowing us to do that together. In past math, like a decade ago, you would have learned how to do it algebraically one year, and then the next year came back to the same math and learned how to do it geometrically, which is dumb. You might as well learn both at the same time. All right, so does that make sense for 21, 22, Al?
Yeah.
Sweet. 23. Biodiversity. The function population at, what is n? N months is 10 times 2 to the n divided by 4. How many months will it take for the tree frog? Oh, same thing here. So actually, when I think of this, what I'm being told, keep forgetting to drag that down. I wish that that was like a mini smartboard and I could like touch interact with that as well. What they're telling us is p to the n equals 10 times 2 to the n divided by 4 will equal 5,120. So really, what's the base of my exponential function? What's the base of the exponential function? 2. It's the thing being taken to the exponent. I would want to start this. If I'm going to solve this algebraically, Jenny, since you chose this, I'm picking on you. Since we want to do this algebraically, who chose this one? Ava. Sorry, I thought this was Jenny. So if I want to get base of 2, I want to look at this side with can it be evaluated with a base of 2, but I've got something else on the left side that I don't want. I want to get rid of that 10. So what could I do first?
Oh, I put it wrong.
So what do we want to do first here? Divide by 10.
I, for some reason, subtracted 10.
So if we divide by that 10 there, I will then get 2 to the n divided by 4. Oh, this keeps making it really fat. Equals 512. And think of, okay, 512 is 2 to what power? Well, 4, 8, 16, 32. We can work our way up. Or, plug this into Desmos. Has 2 different functions. So, if we set up in Desmos 2 to the n minus 4. Actually, we're going to need to do x. It can normally figure it out, but might as well type x here. And then my constant value of 512.
It's n divided by 4.
Ah, it is divided by my bad. That would help. Way zoomed out. And where you put your cursor is where it zooms, which is one thing I really like about Desmos. And it's at 36. Yeah, so if I put my cursor down here, I zoom down here. Where I put my cursor, I zoom out from that center point. So where I put my cursor, I zoom in there.
So it's 36 months.
Yeah, so since n represents months, it would be 36 months. And notice once you click, like you're trying to find the intersection, so if I click slightly off the intersection, it will then put the point where it needs to be, if I'm zoomed in far enough. And if you're not zoomed in far enough, then zoom in closer. Always look at what it's telling you and how you can relate those values. Anybody for 24? All right, 5, 6. Okay.
On the practice number 34.
Any 5, 6 from the front page. So I'll get to your problem in just a second. 34. So it says a geometric sequence has an initial value of 3, a common ratio of 2. Write a function to represent this sequence. So geometric sequences are interesting because it's continuous multiplication. Where we're used to like linear functions and things like that have a continuous addition or a common difference as opposed to a common ratio. My screen is still frozen. So, if I start with 3. Let's just write this out. So I have some geometric sequence. Let's call this A of n. And that's going to be 3 times 2 to the every time that goes. Right? Now let's check that. That would be 3, then 6, then 9. Well, but this, if I do times 2 to the x, this would have happened on the first time. So this doesn't actually work because if I plug in a 1 here, I don't get a 3. So what can I do to the exponents to fix the fact that I don't want that to happen the first time I do this? Jenny?
X minus 1.
We now instead make this x minus 1 because on the first time, 1 minus 1 will be 0, and this will become 3. Then 2 minus 1 takes it to the first power, and 2 to the first power doubles it once then. This is not. You guys are allowed and encouraged to tell me when mistakes happen. What about a 3? If I plug in for my third term, 3 minus 1 is 2. 2 to the second is times 4. 3 times 4 is 12. And this is doubling every time. So our function to represent that has to either be 3 times 2 to the x minus 1, or we have to compensate some other way that this doesn't happen. So we could actually, there's another function option here. Erase some of this extra stuff. There's another option for the function that we could use. We start at our initial term and use the input minus 1, or we have the option, let's go ahead and use some purple. Let's say G sub n, a geometric sequence. What if I want to be able to use times 2 to the x? I don't want to have to use that x minus 1 because I don't like it. Then it's going to double to get to 3. Bless you. This is where we have to use the 0th term, which sounds really weird, but the term that came before the first term. Well, to go to my next terms, I double, so to go to my previous terms, I half. So this would just be 3 halves times 2 to the x. Either way that you write that function will be exactly the same when you graph it. These are the same functions. And if you want proof, don't worry, you don't have to want proof, I'll give you proof anyways. 3 times 2 to the x minus 1 is actually 2 to the x times 2 to the negative 1. What's 2 to the negative 1? 1 over 2. What can be combined here? The 3 and the half. They're the same function. It's just a manipulation. Any questions on that one remaining? Yes?
So then for the G and the parentheses, do we just put that like a Y there?
Yes, I mean that you can use any notation that you want. The reason that we switched from just y equals is in function notation. A lot of times we have multiple functions to work with. So we'll have a of x, b of x, c of x, and they all use the same inputs, but they're different functions. So instead of saying y1 equals, y2 equals, y3 equals, we just change letters. So we make it like the name of the function. So if I had like a Jeremy function, I might say j of x. Like we name things. Like the first, I was watching a documentary about the tech race where computers first started. The first Apple to come out was like named the Lisa. So if we had a Lisa function, we might say L of x. So that's, yeah, which is why we changed the letters. Yeah.
33. I'm not actually sure if I need to ask a question, and then my friends will let me borrow them.
I'm not copying, I'm checking if my answer is right.
You know the answer keys are in Schoology.
Yeah, but I don't remember if like I accidentally circled it or if I fixed it and I forgot to erase the circle. Yeah.
So if you are reduced by 12%, what is the remaining percentage of the initial input that you had? So I guess the reduction of how many button presses? Say R of B, the reduced size based off how many button presses. Well, we know we start with a length of 8. And something's going to happen every time we push the button. If we reduce by 12%, what percent do we have left? 88. Not 180, just 88. Remember, we don't have the original and. We actually, this came out of the original minus. So that's where we get that 0.88. So then to figure out what the length on the 5th time, we just plug in a 5.
Okay.
Yep. Other questions on 5, 6? By the way, if you want breakfast, now would be the time to go. We have breakfast going until like 10:15 or 10:30 or something. 5, 6, last chance. You have to be part of you sign up for the breakfast program online. I talked about it last week, but look it up on the Worthington website if you want to be part of the breakfast program thing. 5, 7.
Oh, no.
5, 7. Anything from the front? I didn't hear mumble, mumble, mumble.
Oh, I have mine wrong.
So 5, 7's combining functions. Yeah.
12.
Anything from the front. Before we go to the back, anything from the front on 5, 7. Back, you said 12. Anything aside from 12 won't get stuff captured. Use the clues. Let's go put on my Sherlock Holmes hat. Use the clues to find the functions. Find two linear functions such that the f of g of, f times g of x, not f of g. You'll do that later. Is 8x squared plus 2x. And f divided by g of x is 2 plus 1/2x. The problem with these is that there's options. So we know that we have two things where f times g is 8x squared plus 2x, and f divided by g. So the weird thing is we don't have a constant there, and we do have a constant here. I don't have a constant there. I do have a constant here. This is weird. What have you tried? Sorry, who asked for this one? What have you tried with this one? Is it just like...
I didn't even know where to start.
You didn't even know where to start. You know what one strategy is if you just totally don't know where to start? And this might strike you as odd. So say you're looking at this question on your homework and you're like, well, snap, I just don't know. What could you do? What help tools are there available to you potentially?
Go on
On Schoology, you look at some things. So let's see if anything on Schoology is helpful. I'm not like speaking facetiously. I'm being serious. If you don't know how to solve a problem, because this is a tough one, I want you guys to be able to like use your help tools. So this was in 5-7. All right, so we see that like f times g of x is just f of x times g of x. F divided by g of x is just that function divided by that function. If I click into here, nothing really extra too much. Could what?
I mean, not really like look up the exact problem, but you could
Oh
look
yeah,
up
we could.
a similar thing.
What if we just look at the answer and then figure out how we get there? Because it's not just about knowing the answer. It's about knowing how we got to that answer. So here's my G form start at 16. If we're on about page 66 probably-ish, maybe. Went too far, I think. The simplifying radical is the next one. Combining functions. So they have this. Why? What do you think they did, or what do you notice they did that we maybe wouldn't have thought of? Because of what I pointed out was this didn't have a constant value, and this does have a constant value. Here we divided, here we multiplied. What do you notice about f of x compared to g of x?
F of x will.
I'm going to drag this up onto the TV for a second. Because that's just an option. That's not the only option. But they use not for b. So they use f of x You know what they probably did first? If we want to make 8x squared, we need two numbers that multiply to make 8 and two x's, because x times x makes x squared. So my options then are 8x and 1x. That's kind of lame. 4x and 2x. Or I flip around 2x, 4x, and 8x, 1x, 8x. So I really only have two sets if I want to use integers there. And the 8x and the 1x is kind of lame, so if I choose 4x, my other function has to have the 2x. So when they started building this, what we did in the solution process we can think through is start with just this. Start with what you need to get the first piece of it. Then, what do you still need? Well, I still need a 2x. Well, I've got a 2x here, but these are going to multiply. So right now, I have 4x times 2x. I'm going to go rogue off of what they have. What if I make the 4x the monomial? It's just 4x. And I look at the 2x as what could I do to 2x so when this multiplies, it will get me what I want.
Multiply by 2.
4x times what to make 2x?
1/2.
Ooh, so what about a half? So that will work to get me my f of x times g of x. Now let's look, will it work to get me my division? So we said plus a half out here. By the way. Now if I divide 4x divided by 2x plus a half, what happens when you divide by a fraction? Multiply by its reciprocal. So this is really sorry. No, it's not. So how do we do this? Yeah?
You simplify the 4x and the 2x to make it 2x on top of it. Wait, that wouldn't be right everything.
2 This is an area where lots of people get screwed up. And I'm trying to think of another example that does not involve things like this. I want real values. So let's look at these two different situations. 10b plus 5 divided by 2b. This is really 10b divided by 2b, and 5 divided by 2b. So I get 10b divided by 2b, which that's actually going to give me 5, plus 5 divided by 2b, which is actually going to give me, sorry, not equal, plus 2.5b. Right, we're pretty familiar with that. If I have non-like terms in the numerator, I can divide. It doesn't matter if my terms are like to do the division. But here, is this 10b divided by 5b plus 10b divided by 2? Because then that would give me, well, 10b divided by 5b, and this is like equals with a question mark. So does this turn into 2 plus 5b? And that's if I split it and do each division by itself.
Whoa!
Don't say whoa like it's cool.
Right. I mean, if it were true, whoa.
Yeah, it's not, so.
I mean, you know.
You're stuck. Unless we can factor things out, make things simpler, and figure out a way that we can actually deal with like terms, we're stuck right now. Because I have a monomial on top and a binomial on bottom. So this is where this can quickly become problematic. If I choose a route like this f and g would work out for the multiplication, but when I go to do the division, things get super hairy. Not very nice. If instead of modifying the denominator function, we modify the numerator function, like what they had done, and we had 4x plus 1 here, this multiplication, when distributed, will work. And then the division has 4x plus 1 in the numerator divided by 2x, and I can split that. Excuse me, because the binomial is in the numerator. It's just like this value divided by that and that value divided by that, which then comes out as what I want. So be careful when we're determining our own functions. You want to try to make the function in the denominator only a monomial. Otherwise, things get very difficult. So sorry that was kind of a bigger example than it needed to be necessarily, but I wanted to reinforce you cannot divide by that binomial. You can't do it. You can manipulate it, you can simplify it, you can rewrite it in a couple ways, but you can't just do it like you can in this situation. It does not work the same when it's flipped. So, and they use pretty simple ones, all integers. Just 4x and the 2x, that'll make 8x squared. And then 2x times 1, and then the division works out. Other questions? I guess I should just go back to 5. What was that? 5, 7. So 5, 8. Yes. It's all in the practice thing. Sorry, which one? Anything from the top section, 1 through 12. Anything 1 through 12. So 18 you said?
Mm-hmm.
And then Jen, you said which one?
23.
13. And what one for the back? Actually, we'll get to the back in a second. I'll leave it open for people asking questions. Maybe back there. All right. 18. What are our instructions here? Probably just combine and simplify. Yep. So, what I need you guys to realize when we're working with multiplication, and especially when we're working with roots, I don't know where I heard this or if I made this up or whatever, but have you, well, I didn't make it up. Anyone here play poker? Like playing card games or any games like that? So has anyone ever heard of the term a string bet? So if I'm playing poker, we all know the basics of poker, right? You get a hand, you make a wager, you win or you lose. If you lose your money. You win your money and other people's money. So I'm playing poker, and I bet 2 chips. And then I look at my hand again, I'm like, wait, actually, I want to bet 2 more. That's called a string bet. Most places will not let you do that because you put down your wager, everybody saw your wager, they started thinking about your wager, and then you're going to change things. It's not fair. Multiplication when working with roots is what I call a string multiplication. It's as if somebody said, hey, we're going to have the square root of 2. Oh, yeah, we also have the square root of n squared. But, oh, we forgot we have the square root of 30. And by the way, we also have the square root of n. And then somebody tried to put some things together and clean it up so we didn't have such a string multiplication. But we don't really need to put things together how they are 2n squared and 30n. Those don't have to be connected. We can break it apart just like this, which then allows me to look at things a little bit more simply. Is there a square root of 2 or any piece of 2 that I can take a square root of? Not really. Can I take the square root of n squared easily? I know this is kind of like, who knows whose question this is. But yeah, guys, square root of n squared, that's of course going to be just n. So my radical 2 I'm going to leave as radical 2. My n, I'm going to make n. Radical 30. Is there anything I can do with radical 30? No, not really. I mean, its factors are 2 and 15 or 1 and 30. None of those are perfect squares. So I'm going to leave it as radical 30 right now. And radical n, I can't really do anything with that either. Did it say anything about simplify, use positive exponents or rational? It just said simplify. Sorry, what, Jenny? Just said simplify. So I now have radical 2, radical 30, n, and radical n. Can I do anything here? Okay. The radical 2 and the radical 30 I can combine and make radical 60. Because if I grabbed these and put them together, I could make it radical 2 times 30, just like they had made it radical 2 times n squared. Order is manipulatable. It's multiplication. Commutative property, friends. So I have radical 60 times radical n, which actually I could leave this as radical 60n if I wanted, times n. Now what can be done? This is one of those skills where we want to make sure we're really confident on this. So hopefully you've either already solved this or you're paying attention. Cassie, what do we do?
You can split it into 15 and 4 and 4.
I can split this into the 4 times 15 radical n times n. Radical 4 is now 2 radical the 15 and the n are still stuck in there. This n is still outside, so when I clean it the rest of the way up, it can become 2n radical 15n. Now, I know, depending on your, like, how you approach things and look at challenges, you're like, why the crap are we doing all this? It all comes back around with the manipulation and skills that you need for calculus and trig and all those different areas where we're just doing some skill building. I know this stuff gets kind of lame where it's like not all practical application and not like word problems and stuff, but this is just making sure you understand how to work with the values, break apart the roots, bring them back together, rearrange things, figure out where your perfect square is. This step right here is what lots of people miss, is figuring out there's a piece of 60 that is a perfect square. And to get there, we had to combine the 2 with the 30. That's the hardest part, was realizing I need to combine those values to break it apart again, differently. So that was 18. 23, Evelyn rode her horse in a triangular path. The distance she traveled south. Oh, so this might end up being a facepalm moment. If I take you back to like a 3rd grade test, say maybe 4th grade, and I say, Evelyn rode her horse south. Can you draw a line showing Evelyn rode her horse south? We would draw our line. And I'm like, just trying to be funny. Don't ever think that I'm like talking down to you guys. I just like relating things to the fact that a lot of times we make math harder than it needs to be. So your first skill that you would need to know is that south is down. So if you don't yet know your coordinate directions, on most maps there's a little thing that tells you. Anyone know the memory trick? Never eat soggy waffles. Never enter Santa's workshop. Never ever smoke. I've not heard that one before. That's funny. I don't like never ever though. That's a little weird. I like never enter Santa's workshop. That's the one that I always remember. But or sour watermelons if they never eat. But yeah, north, east, south, west. For what it's worth, north is that way when you're in this building, so west is over there. That's like your Hilliard area. East is that way, like Westerville and Gahanna. South is that way, like Grove City and downtown and all that stuff. So we went south. Now, Evelyn rode her horse east. So we can show east. Now let's care about the map. Evelyn rode her horse 5 times the distance she traveled east. Well, do I know how far she traveled east? No. But since that's what they're referencing us with, make it something that you know. East was E distance. So how far would the south distance be now if we know that south was 5 times east? This will be 5E. So to figure out and you guys missed it. I had on a great shirt yesterday. I'll wear it again so you guys can get the joke.
It really was great.
Yeah. But I said great, not green. But yeah, it was
Great.
Oh, okay. But it was a green great shirt.
Yeah, great green shirt.
What is the 3rd side of a right triangle called? Now, for all the bonus points in the world. We don't do bonus points here at Phoenix. Why is it called hypotenuse? This goes back to the fact I've learned so much being a teacher at Phoenix. One of the things that I've learned is how much I didn't know about language. What does hype mean? So why is it called hypotenuse?
Well, it's because the hypo is under, and the hypotenuse is under the right angle.
The reason hypotenuse, this could win you $1 million someday. You never know. The reason hypotenuse is called hypotenuse, hypo means under, like hypothermia. It is the side under the right angle. That's why it's called hypotenuse. It's under the right angle. So my hypotenuse here, if you want to get all fancy and jump straight to the formula, my hypotenuse C will be the square root of 5e squared plus e squared. Here's where everyone's going to screw up, though. This a squared plus b squared whole situation, c squared equals a squared plus b squared, it squares all of A. It squares all of B. So when we do that and we end up here, what is 5e squared? 5e squared means 5e times 5e, which comes out to be 25e squared. And then e squared is just e squared. And that's a 1e squared for what it's worth. So then c becomes the radical of 26e squared. And you need to figure out how to combine all this and clean it up for an expression for the total distance. Other questions? By me.
27.
Just like root multiplications are a string, root divisions are really a string. So this can be looked at as radical 18y over radical 36y cubed, which can then be looked at as radical 18 times radical y over radical 36 times radical y cubed. We can keep breaking this apart. So then I can look at 18 and figure out, is there a way to simplify that radical into a smaller one? Well, is there any piece of 18 that's a perfect square? 9. And then is there any piece of 36? Well, yeah, it is just 6. So now this becomes 3 radical 2 because we take the square root of 9, bring it out. Radical y just stays radical y, so I can leave it under the radical in the numerator. My denominator is now just 6, but this y cubed, what can I do with y cubed? Yeah, y squared and y. So this will become 6y divided by, or times rad y. What else can I do? What do you mean rationalize the bottom? We don't really need to take away the square root. Like, at least not the next step I'm thinking of. Is there anything that can be combined with anything here? Like, without having to manipulate the top and bottom, is there just anything that we can combine? How?
Divide radical 2y by radical y, we get radical y.
Ooh, close. So remember, this radical 2y is actually, or can be written as radical 2 times radical y, right? Radicals can be broken up or recombined. If that's radical 2 times radical y, then this would be 3 times radical 2 times radical y. And a radical y on top and a radical y on bottom will cancel out, and this will become 3 times radical 2 over 6y. Then my 3 and my 6 can work with each other because these are both multiplying by these values, so I just get radical 2 over 2y. And that's it. Because remember, this is going to go like a step further than we even really need to go. But I'm trying to like overly explain this. this can or could be written as 3 times radical 2 times 1/6 times 1/y. This is why we're allowed to do those, why those rules apply. Because this is just a string. It says 3 times radical 2 divided by 6 times y. But when you divide by a product, you're really dividing by 2 different things. So I know we don't often do this. This is kind of like back in elementary when we look at like how do we break things up. Like 6 is 2 times 3. 2 times 3 is 6. It's the same thing when we're working with these polynomials. We can just break it apart however we need to. So always remember you can break apart each individual piece and regroup as you want to. Other, what, 5-8? Yeah. 37. The equation R is radius of a sphere So this doesn't even matter in the context of this problem, but just to tell you guys, because I seriously saw this on Who Wants to Be a Millionaire. So this is really interesting for spheres. You don't have to know these, but I find the relationship very cool. Surface area of a sphere is 4 pi r squared. 4, 2, even. I think it works out very nicely. The volume is 4/3 pi r cubed. 3 on bottom, 3 in the exponent. I think it works well together. If you can remember these, great. If not, not a big deal. But the question on Who Wants to Be a Millionaire, I forget who the contestant was. But if Pac-Man was a real physical being and was like 20 feet wide, like it was some kind of more complicated problem. And I think it said, and the like little dudes he's eating are a certain size. Like I think you had to solve the math problem. But all you had to do was be able to relate their volumes, and it came down to knowing the volume formula. And I think he phoned a friend, and I forget if he got it right or wrong. But it was on Who Wants to Be a Millionaire. Volume of a sphere. At least I think it was volume. Might have been surface area, but I remember the sphere problem. So, given the surface area, we just have to plug this value in for the surface area, divide it by 4 pi, and figure out what the square root of that is. Does that make sense, Jane?
Yeah.
Can you ask for this one? Yeah. So, I mean, it's really just plugging in and solving. You could even, if you wanted to, use like your TI or use some kind of function. Yeah, I could use like Desmos or something like that to spit me out, so I can just plug in values. So let's say if I use Desmos and I tell it that I want my y to actually equal that square root of my input divided by 4 pi, and they say use 3.14, but I'm going to be specific and use 4 pi. And then I can just tell it when x equals 1256, and when x equals 96, and when x. What happens when I put an x equals on my graph? What kind of line do I get? Vertical or horizontal? Vertical. So when your x equals, we'll make that x value always equal that. So this is modeling, this black curve is modeling your outputs given the input. So here for my green input, my output value ends up being right about 4. for my input of, what do we input, 200? Oh, sorry, so one's a lot bigger, so that was for green. And then yellow, my output's about 5.5. And then blue is way out here. And it'll find your intersection right about 10. Desmos is amazing. So you could, in your TI, like in your graphing calculator, generate a table. And it will, like, you can add tables in here. I forget exactly how to turn my function into a table. There's a way to turn this into a table and then just input an X value and it'll spit out your Y value. You could do that as well. But if all you have is the ability to make the graph, just make the graph and find those intersection points. Other questions from 5.8? Yeah.
38.
Work backwards. So start with this, since that's going to be what it simplifies to.
Oh.
So if it's going to simplify to 2x radical 3. Give me something that we could do to one of our functions.
Could we multiply?
By?
3.
Sure. What's that going to become?
6x.
And that's it. Because remember, this is one term. We don't distribute, because that's not added or subtracted. If we take things to a power, that gets a bit different. But yeah, so just manipulate it 3 different ways. So one way, you just tripled it. And then if we divide that by 3, divide that out. And they have to be radical expressions, so be careful with that. Which actually, so we could even like, what if I guess I didn't even need to erase that. I could change and do like, what if I square this? And that's going to give me something like that, and that's not a radical expression. So be careful. I don't want to just give these things away. And you can check your answer keys to see some examples. And they'll say on the answer key, answers will vary. They just give you a couple examples to get like a taste for what it could be. 5.8. Anything else? Going once. Going twice. I upgraded my water bottle game. Five, 9. Oh, you logged me out, really? Piecewise. All piecewise means is broken function. So where one function actually needs multiple functions to describe that behavior explicitly. Jenny.
Like 5 or 6.
I only need 1, 2, 3, or 4. You can use Desmos to help with those if you need. So what do you mean? Like, what do you need from 5 or 6?
Really, right now how like you start on, like if it's x equals like is greater than or equal to 3 or whatever, you start on like that x value on the graph.
Yeah.
But, like, I don't know where to get like a starting point.
What do you mean a starting point?
Like where to start for your graph.
think I have graphs in here, but I can't get to my buttons because that thing is blocking me.
Can't you move it?
Yeah, but not while it's recording. All right. Once this loads, so here's the deal with your starting point, Jenny. Your starting point should be the split in the domain. So where that split in the domain happens is where you want to start your graphs. Or pretty fun. So make yourself a table for both functions, and I actually so f of x you can say is g and h of x, if that makes things easier for you. So I then say, well, okay, so it doesn't really matter because it's only going to operate in certain spaces. So to keep with how they represent it, if I have an x and an f of x, when my x is below 3, it has to be this function. When my x is 3 or greater, it has to be that function. So if I start below 3, let's say 0, 1, 2, 3, but I could really start at 3 and then work back, and then I can go forward. So if I'm at 3 on this function, so let's go ahead and actually do 2 so we can be on that function. Negative of 2 plus 2, well, that actually makes 0. Negative of 1 plus 2, well, that actually makes 1. Negative of 0 plus 2, well, that actually makes 2. But now, to go 3 or beyond, I have to change to this function behavior. So now 2 times 3, 6 minus 4, gets me 2. But there was a point where there's a point that I can't use, but I still graph it. I just graph it open circle since I can't use it. So we still actually have to calculate where the 3 would be from the other function, but we then just make it open. So the negative of 3 plus 2, this would give me a point 3, 1. So here's where people get goofed up. 3, 1 is an open point. Then 2, 0 is a closed. 1, 1 is a closed. That's probably supposed to be negative. No? Plus 2 is 0. Negative 1 plus 2 is positive 1. Is that negative 1? That is negative 1. This open circle is supposed to be negative 1. My apologies. That is negative. Open circle. Closed. Closed. It goes that way. For my green values, now I plug in 4, 8 minus 4, 4, 10 minus 4, 6, 12 minus 4, 8. So I start at my 3, but then I'm at my 2. It is perfectly fine that these are in 2 different places. I've had multiple questions from people asking, like, I did something wrong. These aren't at the same place. Yeah, that's fine. Because your function completely changes behavior there. These are very different. You have a constant of 4 subtracted, a constant of 2 added, a coefficient of 2, a coefficient of negative. So this then starts its behavior and goes more dramatically. And that is our piecewise. Broken graph. This point just can't be used by both at the same time or it's not a function. So that's why this has to be open when that is closed. But we can't not care about that point because we have to use this line all the way up to that point. That's why there is a point where you kind of look at both options for 3. Any other 5-9 questions? The absolute values are always going to look like a V, pointing up or pointing down. Shifted depending on the behavior. Play with Desmos if you want to get more comfortable with what shift behavior does. Any other questions? Chapter 5. Any and all of Chapter 5. Once. Twice. Sold. So if you are feeling comfortable with Chapter 6 and want to take that assessment, or Chapter 5 and want to take that assessment, you may. Otherwise, I'm going to move into Chapter 6 and take questions on our data analysis. What practice forms did we have for Chapter 6? Jeez.
Oh, they were K's actually.
They were K's. You got me there. I'm just going to open up all of these.
When we turn in, like,
So hold on. So I'm going to stop the video and then start a new one for Chapter 6. So this is everything for the Chapter 5 review. If you're at home and you weren't in class, please come in and take your assessment. We need to stay on schedule. So let me know, email me, text me, call me if you have any other questions, comments, or concerns.